Hello! Today we're going to talk about magnetic fields. And although I personally find magnetic fields a bit more complicated than electric fields, interestingly we know about them for a much longer time. Most knowledge of electric fields comes from the 19th and a little bit 18th century. However, about magnetic fields, there's notions of them even as long ago as in the 4th century before Christ, when Chinese writers talked about these forces between so-called what we now call magnetic materials and iron. And even in Europe, we are using compasses since the 14th century. And in some sense, it's obvious why this is the case. Because the magnetic fields are omnipresent, right? The Earth itself is a magnet and we have the Earth magnetic fields. And we can use that to navigate our planets, as people have done very wisely. I find this quite interesting because it shows that we have been actually using the magnetic field for a much longer time than we understand it. So sometimes makes me wonder. But nonetheless, since we understand it better, we can use it also in a more subtle way. Another place where we see magnets is, for example, in the picture on the right, where you see basically a typical old-fashioned magnet, which is a metal where there's a north pole and a south pole. Another way to create a magnet is through a wire. So if you put a current through a wire, actually a magnetic field arises. So what are the properties of such a magnetic field? So for example, what people found out at some point, and this was in the 19th century when people started to play with currents through wires, they found that when there is a wire and it does not carry any current, so there's no current flowing, there's no field. No magnetic field. So the magnetic field we detect is just the Earth magnetic field. However, interestingly, if there is a current now putting on the wire that starts to flow, we can observe a change in direction of the magnetic fields. So there comes a magnetic field. And more interestingly, or equally interesting, is if we put the current in the opposite direction, there is a magnetic field in the opposite direction. So apparently, we can create magnetic fields by flowing currents through wires, and they depend on the direction of the currents. So what creates this magnetic field? And what is sort of the component of this magnetic fields? So if we think about the fundamental particle magnetism, it sort of already makes it somehow clear why it's a bit more complicated than the electric fields. In the electric fields, you have an E field that has a direction, so it's a vector, we talked about that before. And that E field creates a force in a certain direction, in the same direction actually, on an electric charge. However, what about a magnetic field? Is there something like a magnetic charge? Well, the simple answer is no. There is no magnetic charge that we know of right now. So that would be the so-called magnetic monopole. And this is interesting because there have actually, what I just read, that Mr. Van Hoof, Professor Van 't Hoof, he's our Dutch Nobel laureate in physics, and he has actually predicted monopoles, but they have never been built. So people state that if you manage to build a monopole, this is your ticket to Stockholm. But so far, no one has managed. So the smallest particle that we know in magnetic field is a magnetic dipole that always has both a north pole and a south pole, and that is the ultimate fundamental charge, if you want, for a magnetic field so far. So, in a way, the electric charge is also the fundamental particle of a magnetism in the sense that it basically is necessary for a magnetic field. So if we think about the forces created by a magnetic field on an electric charge, we can make several observations. So if we make the charge on a particle in a magnetic field higher, the force will be higher. If we make the velocity of the charged particle in the magnetic field higher, the forces will be higher. If the magnetic field itself is higher, the force will be higher. If also the angle between the magnetic fields and the particle is large, the force is higher. So here we see one of the big differences between an electric and a magnetic field. In the electric field, the force on the charged object is in the same direction as the electric fields. If it is a positive particle, if it's a negative, it's in the opposite direction. However, in the magnetic fields, this is not the case. So basically, if a particle moves through a magnetic field, if it moves in the direction of the magnetic field, there is no force. So this is this angular dependency. So more specifically, the force is zero if there is, again, if there's no charge, if there's no magnetic field, but also if there's no motion or if there's no angle. So there's this more geometrical effect going on. So in the end, what that tells us, if we just think again of the scalar value of the magnetic force, it says, it comes back to the force is the amount of charge it has multiplied with the velocity of the object, the magnetic field, and the angle between the magnetic field and the motion. So if it's perpendicular, this is the maximum angle, you get the maximum force. If they're in parallel, there's no force. And I'm not going to talk about it today, but what you'll learn next year actually is how to formally describe this. So how to formally describe the vector force, so not the scalar, so the magnitude of the force, but actually the direction. And this is what you're going to use outer product for, but outer product is something that you will learn in your math courses next year. So for now, I'll just tell you that the vector of the force is a function of the charge of the electron, of the direction of the velocity, and the direction of the magnetic fields. And how exactly that's formalized, you'll learn later. However, I suppose you also know, we have the right-hand rule. So that's at least going to tell you in which direction the force is going to be, up or down. And I guess you've seen it many times before, but what you want to do, if you want to use the right-hand rule to determine the direction of a magnetic force for a positive charge, what you do is you draw your magnetic field in the right direction, you draw your velocity in the right direction, and then what you do with your hand, you go with your fingers from your velocity towards your B fields. And if you do that, you'll see in this case, for a positive charge, it's moving upwards, because if I do this, you see that I'm going from B to V, that's not supposed to happen. And if I have the one below, I go from V to B, I go downwards. So this is the right-hand rule, at least gives you a handle on how to predict which direction it is, although we don't use the outer product yet. So what is important to realize is that this is for a positive charge. So if you have a negative charge, it will actually be in the opposite direction. So it's good to realize if I have a positive and a negative charge, move in opposite directions through a magnetic field. So some units and numbers. The magnetic field is actually given in Tesla, and this is named after Nikola Tesla. He's a Serbian. He was actually a self-taught man. He didn't have enough money to go to university, but he was the one that actually was the founder of the AC current system. And for that, he got his magnetic field named after him. Also, 1 Tesla is basically what we typically use. It's interesting to also know that we have the unit Gauss, and Gauss is 10 to the power of 4 Tesla, and that's actually typically the size of the Earth's magnetic fields. And this Gauss is actually named after the mathematician Carl Friedrich Gauss, and this is also someone you will encounter next year, because we use Gauss' law to calculate actually the sizes of electric fields through a very smart mathematical trick. And actually, what I found interesting about Mr. Gauss, because sometimes you think that these are all sort of very heroic men, and you look up to them. But what was interesting to read is that he actually had 6 children, but he had 4 boys. But he basically told all of them that they are not allowed to go into mathematics because they would all never be as good as he, and they would only lower the standard of the family. So I was like, well, maybe it's not so bad that we don't all have a father like Carl Friedrich Gauss. Well, I guess enough about that. With that, our module ends. Wish you good luck with your exercises and with the examples, and I thank you for your attention.